Consider the following problem where we are asked to find the magnetic field B sub P in both magnitude and direction at the origin, the point P. Two wires of 20 amperes each are going out of the page. Those are the two wires that are coming out of the page, and two wires are going into the page. Now the first thing you need to do in a problem like this is to figure out the directions. Without the directions, there's no point in even starting this problem. So let's use the right hand rule. The right hand grasping rule of BO sub R says that if you start by grasping this wire, then you see that the magnetic fields go in concentric circles. As a matter of fact, the radius of these circles is going to be 5 centimeters because 3 centimeters and 4 centimeters constitute a 3-4-5 triangle. So the other important realization you need to have is you don't have to be fooled by the geometry of this thing. This may look like a rectangle, but what you're really concerned about is the direction of the magnetic field. That magnetic field will be tangent to the circle, that this big circle here that goes through this point P. In other words, the magnetic field you're going to draw is going to be a 90-degree direction to the line joining the two things. So this is the true direction of the magnetic field. It's going to make a 90-degree angle there. Now let's see what happens with this one. Well, that's going to go like that. So to find out how that looks, you draw a line joining the wire and the point P. Now you're going to have a circle that goes like this, and that circle will make a 90-degree, the radius of that circle and the magnetic field will make a 90-degree angle. So these 90-degree angles are extremely important in magnetism. The direction is not, you can't just draw a random vector in any direction you please. You have to respect the directions very carefully. So we can actually start thinking about angles now. Seeing as the important angle is this one, right? Because if I call this angle theta, then because this angle is 90 degrees, this angle is going to be 90 minus theta, and then this angle is automatically going to be theta also. And this angle is also going to be theta. So you can already see that the important angle is not this theta, but rather that theta. So that's the first piece of insight we get. Now what about the 10 ampere wires? Now if you look at the 10 ampere wires, they're going to have the thumbs into the page. So in fact, the directions of the 10 ampere wire magnetic fields are going to be exactly the same as the direction of the 20 ampere magnetic field. So we're really in good shape there. I'll draw a smaller vector here to indicate the directions of the 10 ampere magnetic fields. So here also it's the same thing. So now we have got the directions all squared away nicely, and all we have to do now is to calculate the vector result. So this first step, the drawing of the figure and to figure out exactly what's going on, is like the make and break step. If you do something wrong here, it doesn't really matter for you to continue doing whatever you're doing. The problem is simply wrong. So I would say spend about half your time deciding how the directions are going to go. In the homework problem, for example, don't randomly draw some vector. Just figure out very carefully how the direction is going to go, because everything else will depend on that. So the magnetic field of an infinite wire is given by the BO sub R law formula. Magnetic field is equal to mu naught I over 2 pi R. That's the standard formula. And that's also found in your formula sheet. If you want to take a look there, you can find it in your formula sheet also. We're going to use that result. The distance r is the Pythagorean distance r, so that's going to be 5 centimeters, because that's, as I said, a 3-4-5 triangle, and you get 5 squared equals 3 squared plus 4 squared. So that's a 5 centimeter distance, and you have to convert it to meters, of course, when you're using this thing. And the net result of adding all these things vectorially is B net. Now remember, the sine theta components, with the theta being this one, cancel out for both of the magnetic fields, and the cosine components add. So I'll be adding the cosine component, so it's going to be 2 times, because I have above and below. So 2 times mu naught of the first wire and the second wire, because remember I told you that they're contributing in the same directions, so we don't really care, divided by 2 pi r, so that 2 cancels with that 2, times cosine theta. Done. Now all we have to do is sub the numerical values, and the total result, by the way, is along the x-axis, because the only component left is the x component. So we can even go ahead and write b net x, and then say b net y equals 0. So let's put the values in. The value of permeability mu naught is 4 pi times 10 to the minus 7 Tesla meter per ampere. The current I1 plus I2 is just 20 amperes plus 10 amperes. Cosine theta. Now, you don't really have to find out what theta is, because all you need is cosine theta. Let's look at this triangle. That's 5, that's 4, and that's 3. Cosine theta is adjacent, which is 3 over hypotenuse. So cosine theta is just 3 over 5. Let's run away with that. Divided by pi times the radius or distance from the wire, which is 5 times 10 to the minus 2 meters. We have to convert the 5 centimeters to meters. Okay, and now let's see. I don't have a calculator handy with me, so hopefully my prayers will be answered and I don't have to do much. What I like to do first is to see the units working out. That's always my first concern. Yes, I get Tesla, which is fantastic. So what I do in case I don't have a calculator is move all the numbers to the front. So I have 4, I have 30 because that's 20 plus 10, and then I have 3 divided by 5 from here and a 5 from there. So put all those things together, and then I look at exponent next. That's 10 to the power minus 7, and there's minus 2 downstairs, which becomes plus 2 when you take it upstairs, and then the units. So numbers, powers of 10, units. You'll never go wrong like this. And here it's just a matter of swinging it. So let's see, I have 30 over 25. That actually, let me try this. I go 5, 6 or 30. And so I'm going to get 6 4s are 24. And 24 3s are 72. So I'm going to get 72 over 5, which is the same as 144 over 10. Ten times 10 to the minus 5, because that's what I have there. And I can take this 10, I can borrow the 10 there and write this as 144 microtesla. In this manner, I have solved this problem without so much as lifting a finger and pressing a calculator button. You can, of course, use a calculator, but it's not going to give you any different answer, and this answer is absolutely exact.